All right, good morning, everybody. Hope you are all making good progress in the project. And I'm going to be holding an office hour in my office right after the lecture today from 11 to 12. So if you have questions you want to ask me, you are welcome to join me in my office. So it's in building 33, room 412. So building 33 is it's kind of the opposite corner from here. It's where Massachusetts Avenue intersects with Vasa. So building 33 is over there. My office is on the 4th floor. Room number is 412. All right, so today we are going to be continue discussing our finite difference. Actually, this is the last lecture on finite difference. And after this, we are going to basically apply finite difference to a case where we see is actually where finite difference is not so applicable, and we'll introduce why we are going to finite volume. And the motivational case is in some differential equations, actually finite difference would stop working. Okay, but before that, we'll continue on the cases where finite difference would actually work very well. And this is for Poisson's equation. And Poisson's equation is actually almost exactly what you'll be solving in the project, right? So basically, we already discussed how to approximate a derivative with arithmetic. And the differential operator we use is very similar to the ones we used in the heat equation, except you have x and y directions. So if you derive an error that is on the order of delta x squared in the heat equation, over here you have the order of delta x squared plus order delta y squared, right? So essentially, if you look at how much error am I causing, again, tau, the approximation error, would be equal to the difference between our finite difference approximation, delta x squared, u of I plus 1 j, plus u of I minus 1 j minus 2 ui. So that's our uij. So that's our approximation to the second order x derivative. We also have a approximation, well, to the second order y derivative, and the indices should be ij plus 1, ij minus 1, and again minus 2 uij, right? So that's our approximation to the second order derivative. If we subtract that from the Laplacian operator, the analytical Laplacian operator, which is the second derivative in x plus the second derivative in y. And remember, we have to apply this numerical and analytical derivative to the same function, right? So if we apply them to different functions, of course we get different values, and this does not represent the true truncation error. The truncation error means if we apply different operators to the same function, how different would the result be, right? So that's the truncation error. That's how much error we make to the approximation. And no matter what kind of equations you solve, as long as you are using finite difference, the truncation error analysis is the same. You plug in all the Taylor series. But over here, the Taylor series, of course, it has to be in x and y directions, right? Do we all know how to expand the multidimensional Taylor series? Oh, I mean, if you don't, you can look at Wikipedia for how you expand it. I'll just try expand it in very simple terms. So for example, ui plus 1j is actually equal to u of whatever xi j is plus another delta x, and also yij. Right, so that's what we mean by u of I plus 1j. And now we expand this around u xij, yij, right? So that's what we choose to expand our terms. It's actually the simplest choice over here, because all the points I plus 1j, I minus 1j, ij plus 1, and ij minus 1 are only delta x or delta y away from this point. So everything coming out of the Taylor series expansion is proportional to delta x or delta y, or delta x squared, delta y squared. There is no like 2 delta x and 3 delta y squared to deal with. right? So if you have a larger stencil, then you're starting having to deal with a multiple of delta x or delta y to the certain power, and the number starts to get complicated. All right, so here, this term and the first order derivative term is actually going to be delta x times the partial derivative of x. And if there is a plus delta y here, you would have a proportional to delta y times the y derivative. But here I have 0 times the y derivative, right? Because the delta y is actually equal to 0. The y coordinates are the same for the evaluation point and the expansion point. So the y derivative is going to be 0. And then I have half of delta x squared term, second order derivative, plus, well, there is actually a delta x, delta y term, but delta y is actually 0, right? And 2 and over 2, so it actually cancels. This is the cross derivative term, right? Which again is 0. I mean, but if you actually have a more complex stencil with coordinates that are not exactly aligned with the xy direction, you would have a non-zero over here. All right, so this is basically how we expand the Taylor series expansion in multiple dimensions. Oh, yeah, delta y is actually 0. So we also have this, and basically plus O delta x squared and O delta y squared, O delta x delta y. But this, all the three terms, oh, actually, sorry, it's actually the big O should be cubed, and all these four terms, I mean, these are kind of representing the even higher order Taylor series terms. But these terms are actually on the same order if you refine isotopically. What does that mean? It means every time you make delta x smaller, you also make delta y smaller in a proportional way. So if you refine isotopically, then you don't have to really write down all of these O terms. You can just say plus O delta x cubed, right? I mean, the assumption is isotopic refinement. So now you perform all the Taylor series expansions, and that's how you derive the truncation error. And here, basically, the truncation error here is going to be derived to be O delta x squared plus O delta y squared plus O. I don't think here there is O delta x delta y, but like you write it like this, or just the O delta x squared for isotropic refinement. Okay, any questions on the Taylor series for getting the truncation error? No? Yes?
Wouldn't it be delta x to the first since delta here you have cubed and divided by delta x squared, or are there other terms that cancel but we're not seeing?
Where?
The order, the final order, because your order is x cubed and then you're dividing by x squared. Is that just because there's other terms that canceling that we're not seeing? Or?
That's a good point. So if you simply follow this, you find out that everything is going to cancel. Okay, and in order for you to actually figure out the error term, you actually have to expand further, right? Good point. Right. So so like this is what we actually discussed the last time. If you do the Taylor series analysis and see everything cancels, that is sufficient to actually derive the scheme to figure out if the scheme is consistent or not. But it means you are insufficient. You have expanded insufficient terms to actually figure out the leading truncation error. That means you have to expand things further. Over here, if you just plug in this Taylor series, you find out everything cancels. That means you have to expand further. Yeah, good point.